Hey everyone, guess what we're going to do today? Yep, you guessed it. We're going to do more simplifying rational expressions. Yeah, there's a lot to it. So yeah, we're going to spend another lesson here, and kind of breaking up these lessons I think is a good thing because like I said, there's a lot to simplifying rational expressions. There's a lot of little nuanced things that you're going to see from time to time. And I want you to kind of know what to look for when you're simplifying these things, because ultimately when you're doing these problems, you want to get it simplified as much as possible. And, just maybe forgetting to take out a negative or just switch some signs around could have made the difference of perhaps canceling more stuff out. Okay, so let's go ahead and get started here. Let's get right into some of the examples. All right, so example 1 here, let's take a look at this. And just as we've usually been doing, what you want to do is you want to factor as much as you can in the numerator and in the denominator. Now, in the denominator, it might not look like there's much to factor, but there's a little bit more in that denominator than you would expect, and I'll show you what I mean. But that numerator right there, what does that look like to you? That looks like, well, that's a perfect square right there, and that's a perfect square right there. So, and there's a minus sign there, so that tells me that it's a difference of two squares, right? So it's got to be a DOTS. Okay, so a difference of two squares is going to factor like this: x plus 6, x minus 6. And then I'm just going to write 6 minus x in the denominator. And this kind of leads into what I was kind of talking about here, because today's lesson is called simplifying using opposite common binomials. So it sounds kind of complicated, but it's not as bad as you think. But what I mean by this is, if you look at the denominator here, if you look at the binomial that's in the denominator, we've got 6 minus x down there. And that is so close, but not so close to being just like that. X minus 6 and 6 minus x, they're kind of the same thing. And sometimes whenever I teach this, a lot of times I should say, when I teach this, people think, oh yeah, those cancel each other out. And they don't. Because remember, in order to cancel each other out, they have to be exactly the same. Check this out here. This x right here is positive. What's this x? That's negative. There's a negative sign in front of it. This 6 right here is negative. Right there, you see that? And that 6 right there is positive. So those are not exactly the same. So, I mean, they're so close. But what you want to do, if you can, and this is possible, when you notice that you have a binomial that is really super close to being just like another binomial, but not quite, what you can do is you can factor something out of this binomial. What do you guys think that could be? You can factor out what? You can factor out -1, right? Remember, there's ones everywhere, and there's also, when you think about it, negative ones everywhere. So we can factor out a -1 out of that bottom binomial there. Now I'm going to keep the top the way it is. I'm going to write x plus 6, x minus 6. And then in the denominator, what we're going to do is we're going to factor out the -1. And when you factor out a -1, well, it basically changes the signs of everything that it's factored into. So what happens is now the 6 becomes -6, and minus x becomes plus x. Right? And you can kind of confirm that if you kind of redistribute that -1 into there, and you can kind of confirm that that is how that came out. Because what's a negative times a negative? -1 times -6, -1 times -6 is positive 6. -1 times positive x is negative x. And that's how it started. Okay, so we have that -1, -6 plus x in parentheses right there. And then the next thing that I always get from people is like, well, what was the purpose of doing that? It's not really the same, but it is. These now are exactly the same. Now let me explain why that is. Because all I have to do is change the position of those terms, and you'll see how everything kind of cancels out. You'll see. So I'm going to leave the top. Notice I haven't really done much to the top since the very first step. And I'm going to keep this -1 right there. And then instead of writing -6 plus x, I'm going to write x minus 6. Because that's what it says over here. 6 is negative. 6 is negative over here. and x is positive, and x is positive over here. So nothing really changed except for the way I wrote it, but everything still means the same thing. So now the next part of this problem is to start canceling. And so now you're allowed to cancel. Now notice, I'm only canceling x minus 6 with x minus 6. This negative 1 didn't get canceled out. So it was important that we kind of pulled that out. That's now part of the problem still. Now if you remember, when you have a negative in a fraction, especially when we talk about rational numbers, when you have a negative in a fraction, one thing I've taught, or I'm sure I've discussed this several times, is that that negative can float around. It can float around. And one thing that I think I've said this quite a bit, is that I don't like, and you're probably going to hear this from other math teachers as well, but it's not always a great thing to have a negative in the denominator. It's not wrong. It's not simplified either. So what you're going to want to do is you're going to want to get that negative 1 to float up to the numerator like that. And we really don't need positive 1 anymore in the denominator because it really doesn't do much. When you have 1 in the denominator, if you have 7 over 1, well, it just means 7. You don't need to write 7 over 1. We all know that it means 7. Once you have that 1 in the denominator, you can kind of just be done with it. So that answer right there that I just showed is good. Or some people, and it depends on, I think sometimes, especially when you're doing online assignments, but sometimes they ask you to distribute that. But if you want to, you can put negative x minus 6. That would also be fine. But I think this answer right here, for what we're doing right here, is perfectly fine. Even this, I guess, would be fine for what we're doing. Because, again, we're new to this. This is not an easy skill, and I'm throwing a lot of little tiny things at you. And I know it's kind of stacking up on you, but just kind of go through these and follow that rule of slow and steady wins the race. You're going to make it through these. Let me make sure this is totally clear. The solution, and this isn't really a solution, it's the simplified version of that rational expression, is negative, and then in parentheses, x plus 6. Or you can write negative x minus 6. Both of those answers are perfectly fine. Okay, so now that we've got example 1 out of the way, now you know what to kind of expect with these examples. So let's look at example 2. And there's a little bit to factor in both the numerator and denominator. So let's go ahead and factor the top. Now, what do you notice that we could do in the top? We can factor out a GCF. And what is that GCF going to be? That's going to be 2, right? You can factor out a 2. So let's go ahead and do that. I'm going to write over here. And when you do that, you get x minus 5. And just like the first problem there, we have 2 perfect squares. That's a perfect square, right? 5 times 5. And that's a perfect square of x times x. So that's a difference of 2 squares. So when we do difference of 2 squares, we're going to do it like this. But I'm not going to do this. I'm not going to do it like that because that's not how it's written. It's written with 25 first minus x squared. So what we're going to do is we're going to put the square root of 25 first. So put 5 there, and then plus x minus x. And that could totally be turned around. It could be minus x plus x. It doesn't matter. And just like we were talking about on the first one, you're going to notice that you're going to have a couple binomials that look like they could totally factor out, but they're not the same. These are not equivalent binomials. But we know now, we have a strategy now on how to do that. So what we can do out of this one is we can factor out negative 1. So I'm going to leave the numerator the way it was, 2 and then x minus 5. Now what I'm going to do, once I factor out that negative 1, is I'm going to stick it over here. And then I'm going to write 5 plus x. And then the factoring out the negative, well, that 5 becomes negative 5. And that x becomes positive x. Remember, because when you factor out a negative, it changes the signs of everything that is in that group. Now, if we clean this up a little bit more, okay, cue in on something. That negative right there, and like I was saying before, those negatives can kind of float around. So we can take that negative and we can put it up in the numerator. So when I rewrite it, I'm going to write negative 2, and then x minus 5 right here. And then I'm going to clean this up a little bit too. Instead of writing 5 plus x, I'm going to write x plus 5. Why? Because I can, and it looks better, right? And if you want to leave it 5 plus x, go ahead. And then instead of writing negative 5 plus x, I'm going to write x minus 5. And now you can totally see that these binomials cancel each other out. And that's all that canceled out on that problem. When we write our answer in simplest rational form, basically in simplest form, that's what we get. Okay, now moving on to example 3 here. We're going to factor the numerator and denominator as much as possible. And is there a GCF here? Yes. We can factor out 2 out of the numerator there. So when you factor out a 2, you're left with 1 minus m. And then in the denominator, oh, you know what? You can also factor out a 2 out of the denominator. I notice there's a 2 here. 2 is a factor of itself, and 2 is a factor of 4. So we can factor out a 2, and we're left with m squared plus 1m. I'm just going to write m minus 2. But now remember, just because you factored once doesn't mean we're through factoring. Right here, this, we can use that product sum method to factor that out. So remember, our 2, that's our product number. So there's not a ton of factors for 2. I mean, there's only one factor pair that makes 2, 1 and 2. So it's got to be 1 and 2. 2 and 1 there, doesn't matter. And our middle term, that's our sum, right? That's the sum. So we want a sum of 1. So how do we make 2 and 1 into 1, positive 1? Well, we better make it like this. Plus 2 minus 1. That's what we have going on there. And as you can see here, the common recurring theme here with these problems is that you always end up, and this is not going to happen every time you do one of these problems, guys, but today we're at least practicing this skill. But you're going to notice the common recurring theme is that these two binomials, this one and this one, are very similar to each other, but they're not the same. They're not the same. You can't just cross them off. I know some people end up just saying, well, Mr. Oliver, is it okay if I just cross them out and I put a negative somewhere? And I tell them, yeah, that's fine. But I really want you guys to understand, as you know, I really want you to understand what the algebra behind all this and understand what's going on. So what I'm going to do, I'm going to take that top 1 minus m, and I'm going to factor out negative 1. Okay, so that's what we're going to do. Now, in factoring out negative 1, that 2 is going to become negative 2. And then I'm just going to go ahead and write this as m minus 1. And then I'm going to write the denominator exactly the way it was before. And now you guys can totally see what can cancel. So on this one right here, the m minus 1 cancels. Now on this one, the m minus 1's cancel perfectly now. And that's not all that cancels. You'll notice on this one here, we've got negative 2 and 2. So those can both be divided by 2. So negative 2 divided by 2 is negative 1. And 2 divided by itself is 1. So really you don't need that 1 anymore. So all that's left, now notice in the numerator here, let's kind of pay attention to what's happened in this numerator. All that's left, now the m minus 1 canceled, the negative 2 canceled. All that's left is negative 1. So that's all that remains in that numerator. In the denominator, there's a 1 there, but we really don't need to show that. So I'm just going to write m plus 2. And that is as much as you can do with that problem. Now, before you guys close off everything, I'm going to go back. I'm going to annoy you a little bit here. But there was one thing on the previous day's lesson. We talked about these things called restricted values. You know, we're going to start calling them domain. But restricted values, you know, especially when you're talking about rational numbers in particular, are there any restricted values? Now, when it comes to restricted values, you definitely have to pay attention to when there's a denominator. When there's a denominator. Now, if there's no denominator, because like on this particular problem right here, when we simplified it, we didn't get a denominator. I mean, I guess there's a 1 there, but I'm talking about like when there's an x in the denominator. That's what we're talking about. But when there's a denominator, we have to be very, very careful that we don't get a certain number in that denominator. And you all know, I bet you're reading my mind right now and thinking, I know what that is. That's got to be a 0. Because there can't be a 0 in the denominator. That's definitely, I'm not saying 0 is a restricted value, but you definitely don't want to have an answer or a solution where the answer comes out to 0 in the denominator, because that's going to throw everything off. That's considered undefined, right? That's impossible in math to have a denominator of 0. It's impossible to divide by 0. That's undefined. It's okay to have a numerator of 0. It's okay to have the 0 up top, but what you really want to focus in on, laser focus on that denominator. And if you have a 0 in there, that messes everything up. So on the first example right here, and I'm sorry, this is such a mess, but on the first example, these were our solutions, and none of those had a denominator. So we didn't really have to worry about that. There's no restricted values at all. So you could just say none on this one. There are no restricted values, right? There's nothing that you cannot use. Everything is up for grabs on that problem. On number 2, now number 2 actually has a denominator. So that's the one I'm talking about right here. It's got x plus 5 there. So if you're looking for the restricted value there, what you're going to do is just think, okay, what value will make that denominator equal to 0? So all you have to do is set that equation, whatever that expression is in that problem, you want to set that expression to 0 and then solve it. And this is a simple equation, and you get x equals -5. Now I'm not saying the answer to this problem is x equals -5. What we just figured out there was we figured out a restricted value. And so what I'm going to say is that, I know this is kind of weird, but we're going to say that x cannot equal -5. That is one value that if you put that in there, in that solution, that's one value that is going to screw that up. It's going to make that undefined. It's going to make that an impossible solution, which is what we don't want to get. We don't want to get a 0 in the denominator. So I know we just said x is equal to -5, but what we're really looking for is what can we not use in that denominator? And what we could not use was -5. Everything else is still on the table. Everything else, you can use a 6, you can use 0, you can use negative numbers, you can even use decimals and fractions and stuff like that, but the only number that will not work is -5, because -5 plus 5 makes 0. And then focusing in on this last one here, the restricted value. For this one, we definitely want to look at the denominator, and we have m plus 2. And what you want to do is you want to just figure out, okay, well, m plus 2 equals 0. So what plus 2 makes 0? Well, that's really easy. Excuse me if this is hard for you, but I think it's easy. But m equals -2 on that one. So we just found our restricted value right there. So we don't want m to equal -2. So that's your restricted value on that particular problem right there. And with restricted value, that's just another way of calling it domain. What are all the possible x values? I know this one particular problem we were referring to the m, but that's what we figured out. We figured out what are all the x values that are possible there. And that's that's one number right there, -2. If you put that in there, that's going to mess things up. -5, if you put that there, that's going to make that 0. And on the first one, there was no restricted value. Everything worked. All right, now your homework, your assignment is to complete these 3 problems, okay? So complete those 3 problems, and you don't have to print out this sheet, but just either write these out on another sheet of paper and take a picture of it and send it to me, or print this out, scan it, take a picture of it. I don't care how you do it. I don't care if you, like I said before, I don't care if you write these on a back of a Dunkin' Donuts receipt, as long as you show me that you did it. But do these problems, as well as figure out the restricted values. The point here for these problems is to get it in simplest form. Okay, and I think every one of these, I picked a problem that will kind of work out the way our notes did. And that is it. Okay, hopefully I didn't confuse too many of you today. But again, we're still on that path of simplifying rational numbers. There's a lot to it, as you can see. This is, this is kind of a good culmination of all of your skills in algebra, kind of all coming together into one. This is an end of the year unit, and these are things you're going to see, I think, next year as well, and as well as into high school math. Okay, guys, so that does it. Everyone have a great day. Have a great weekend as well, and I'll see you guys later. Take care.